everyone, I am Evelyn Buboli and we are the Group 2 with my members Shane Mibulado, Trixie Dadula, Gian Carmelotis, and Kenneth Quizon. So we will be discussing about truth tables and tautologies. So for my part, I will be discussing about truth tables. So a truth table shows how the truth value, true or false, of a statement changes depending on the truth values of its part. The lesson shows examples using negation, conjunction, and disjunction. So first is negation. If a statement P is true, then not P is false, and vice versa. Think of it as flipping the truth value. So negation simply means not. It's like reversing a statement. So if a statement is true, its negation is false. If a statement is false, its negation is true. So next is conjunction. So this represents and. P and Q is only true if both P and Q are true. Otherwise, it's false. So conjunction means and. It combines two statements and the result is only true if both statements are true. And the last one is disjunction. This represents or. P or Q is true if at least one of P or Q is true. It's only false if both are false. So disjunction means or. The combined statement is true if at least one of the individual statements are true. Double negation. The lesson demonstrates that negating a negation results in the original statement P. This means P and negation of the negation P always have the same truth value. Even though they might sound different grammatically, they are logically equivalent. So double negation means saying not something. The idea is that if you negate a statement twice, you end up back where you started, with the original statement's meaning. So for example, if P is Robert owns a car, then not P is Robert doesn't own a car. And negation of the negation P is not the case that Robert doesn't own a car, which means the same thing as Robert owns a car, the original P. So let's say P is equals to Robert owns a car. Negation of P is equals Robert doesn't own a car. Double negation of P is equals it is not the case that Robert doesn't own a car. Notice that double negation of P essentially means the same thing as P, Robert owns a car. Even though the wording is different, the logical meaning is the same. Double negation cancels itself out. Complex statements. You can combine conjunctions, disjunctions, and negations to create more complex statements. Parentheses are used to control the order of operations. So complex statements in logic are like sentences made up of smaller, simpler statements. We combine and, conjunction, or disjunction, and not negation to build them. Parentheses are super important because they tell us what to solve first. It's like the order of operations in math. For example, P or Q and R, the parentheses indicate that P or Q is evaluated first, and then the result is combined with R using AND. This means open parenthesis P or Q, close parenthesis and R, the parentheses show that we must figure out if P or Q is true or false first. Then, we take the result and see if it's true along with R using AND. The parentheses control which operation happens first. The image shows how to build a truth table for a more complex logical statement. It breaks down the process step by step. To obtain the table above, list each component of the statement on the top row. To the right of any intermediate steps, there is a column underneath each component or connective. Truth values are then entered in the truth table, one step at a time. To create the table, you list each part of the statement across the top. Then, below each part, you have a column to fill and whether that part is true or false for each row. You work through the statement one operation at a time, from the innermost parts to the final result. For example, you'd first figure out the truth values for open parenthesis P or not Q close parenthesis. For each row, based on the values of P and Q, then you'd use those results and the values of P to determine the truth values for the whole statement. Open parenthesis P or not Q close parenthesis and P. You fill in the truth values one step at a time until you have the final column filled out.
Good day, everyone. My name is Gian Carmelotes. So this is my report. Step one. This truth table starts with two basic logical statements and P and Q, each of which can either be true T or false F. All possible combination of truth values for P and Q are lessened. Step one. Add a column for not Q. This column shows the opposite truth value of Q. If Q is true, then not Q is false. If Q is false, then not Q is true. Step 2. Calculate P in view and not Q or P or not Q. Add E to this step. D if the either P is true or Q not Q is true or both. It is only false when both P and Q are false. These steps help us understand how logical expressions change depending on truth, the values of their component. So step 2 explanation. In this step, we're combining two logical expression using an operator. Especially, we were talking the result from steps. One, which is P, V, not Q. That is P or not Q. And combining it with the value of P itself. The expression becomes PV not Q. P which means P or not Q and P. To understand this, remember the ORV operator is true if if at if at least one part is true. The not operator reserves the truth value of Q. The and operator's value is only true if both sides are true. So in this, so in each row of the truth tables, you already have the value of P and Q, P, V, and not Q. You apply the AND operator between them. The result is the truth value of P, V, and not Q. These steps help to narrow down the truth value to when both the original condition. These steps helps to narrow down the truth values to when both the original condition P and the broader condition P or not Q are simultaneously true. Sa step 3 explanation, these steps represent the final truth table for the logical expression P, V, not Q. P which means P or not Q and P. The table shows all possible truth values for the variables P and Q, and it breaks down how the full expression is evaluated step by step. P and Q represent Basic dance how full expression is evaluated step by step. P and Q represent basic proposition that can be either true T or false F. Not Q is the negation of Q, meaning it has the opposite truth values. P and B, not Q. Read as P or not Q combines the truth values of P and not Q using the OR operation. P and V and not Q is the final expression which combines the result of P and V and not Q with using the AND operation by evaluating all combination of truth values for P and Q. The truth tables help us see when the entire expression is true or false. It is a systematic way to analyze the logical behind the expression.
Hi, I'm Kenneth Quizon and today discussing about my part. This slide show how to make our truth table for the logic expression. P, disjunction Q, disjunction non-P and Q means not and that this means or means and you list on combination of the P and Q. True, false, then step by step is the table of the solved expression. At the end, the result is only true with both P and Q are false. Bottom line, all three expression P disjunction Q, P conjunction Q, P disjunction Q, and P conjunction Q give the same result. They are logically equal. This slide explains how to make a truth table for the expression P conjunction Q and disjunction R. Since there are three variables P, Q, R, and we need 8 rows to show all possible combination for all truth values after listing them, we follow the same steps as the two variables to complete the table. This slide shows how to build a truth table for the expression non-P and disjunction Q, disjunction non-P and disjunction Q. It's a list combination of P and Q, then adds columns step by step and find the final result. The table shows that a three expression P conjunction Q and conjunction P and Q give the same truth values, meaning they are logically equivalent.
Good day, Mama Pet. I am the next presenter, Trexie M. Lodola. So, for today, we tackle about the solutions of example number 1. We will use a truth table to compare the truth values of both statements. First, column 1 and 2 lists all possible truth values for the propositions P and Q. Columns 3 and 4 shows the negations. These are simply the opposite of the values in columns 1 and 2 respectively. Column 5 shows P and Q. This is true only when both P and Q are true. Column 6 shows the negations of column 5. Column 7 shows true when either column 3 or column 4 is true. When we compare columns 6 and 7, we see that the truth values are the same for all rows. So in conclusion, since column 7 by laying out these possibilities in a truth table, we can see that the two statements behave exactly the same way in every scenario. This shows us that they are logically equivalent. In essence, saying not A or B is the same as saying not A and not B. This equivalence is a fundamental principle in logic. Move forward about the last topic called Morgan's law. So first law, the negation of a disjunction statement. Same P lor Q equals same P and same Q. Meaning, if you negate the statement P or Q, it is equivalent to saying not P and not Q. In simpler terms, if at least one of the statements P or Q is false, then the negation of their disjunction is true only when both P and Q are false. Next is the second law, the negation of a conjunction statement. Same P and Q equals same P lor same Q. Meaning to say, if you negate the statement P and Q, it is equivalent to saying not P or not Q. This means that If this statement
Hi, I'm Shane Bulado, and my part is I'm going to discuss about the tautologies. So tautologies in logic, a statement represented by an entire column of t values is called a tautology, such as proposition is always true no matter what. Consider the statement, all students study mathematics or all students do not study mathematics. So this is a tautology as can be shown in the truth table by considering the result of P disjunction, not P. So the slide uses the example, all students study mathematics or all students do not study mathematics, showing how its truth tables is always results in truth, thus demonstrating a tautology. So since the entries is final column P disjunction is not P are all true, this is a tautology. In the simplest tautology, we may replace the symbol P with any simple statement whether its true values are known or not. So the example shows that the statement is a tautology because the final column of the truth tables contains t or true values for all possible combination of p and q. A tautology is a compound statement of p and p9 that is true in every possible case. So the example shows that the statement is a tautology because the final column of truth table contains only t or true values for the all possible combination of p and q. Equivalent statement if two professions P and Q have the same truth values in every case, and the compound statements are called logically equivalent word and. In logic, a statement represented by the entire column of T values is called tautology, such as proposition is always true no matter what.